your chapters. I'm going to start with chapter 6, the very last one, on coding, channel coding. You have a preference among the questions, the problems that are posted. 6, 1, 2, 3, 4.
2, 3, and 4, please.
2, 3, and 4.
I think 1. 1 is actually. So, yeah, my question about 2 is they make an approximation where they say the sum of all the terms is somehow equals just the first term. Why is that?
Any one of you have the answer to this question? How come we're taking all the summation? There are multiple terms approximated to just the very first term. What is the summation? That's the probability of a message error.
Can you just go over the whole question while you're at it?
Okay. So the probability. Let me see what the question is. Do you have the question? 6.2. Calculate the probability of message error for a 12-bit data sequence encoded with a 2412 code with a 2412 linear block code. Assume that the code corrects all the 1-bit and 2-bit error, 1-bit and 2-bit error patterns, and assume that it corrects no error patterns with more than 2 errors. Also assume that the probability of a channel symbol error is 10 to the negative 3. This is number 2. Yes.
Chapter 6.
6. What is asked is the probability of a message error. So let me write it down. Total number of bits. P to the power of j and 1 minus p to the power of 24 minus j. So what we have is actually a 24-bit code word. So this is our code word. After coding. So the probability of error in this 24-bit code word is calculated by multiplying the probability of error for each one of the bits if they are receiving an error times the probabilities of the correct reception or detection of the rest of the bits, right? So what the summation suggests is the number of possible bit errors starting from three errors all the way up to 24 errors in the bits we have in this code word. So 3 bits of error, 4 bits of error, all the way to 24 bits, all the 24 bits receiving an error. I've already explained what this summation means and what each one of these terms tries to express. So this is the probability of error in one bit, one of the 24 bits we have here. What is the probability of error for that single bit? That is 10 to the negative 3. So what we have here is 10 to the negative 3, a very, very small number to the power of 3, for instance. Then 1 minus the same value to the power of 21. This is just the very first term for the summation. 24, choose 3. Then the probability of the occurrence of 4 bits of error. This would be the probability of the occurrence of 4 bits in error at the same time times the probability of correct reception of the other 20 bits, right? So just take a look at this first term. We have a very, very small number to the power of 3. Of course, this would be a very small number. How about this term? This parenthesis returns a number pretty close to 1 to the power of 21. So we can just simply approximate the second parenthesis to 1. How about this one? We know that the very first term is a very small number. How about the second term compared to the first one? Now that very small number is multiplied by 1 more 10 to the negative 3 compared to this one, right? So we have 10 to the negative 3 to the power of 3. That's going to be 10 to the negative 9. Here for the second term, we have 24 choose 4 times 10 to the negative 12 times another second parenthesis, pretty close to 1. So comparing these two terms, we realize that the second term is in the order of 1,000th of the first one. It is evident that we can neglect the second term and all the preceding terms in this summation and approximate that with the very first term. In practical examples, practical problems, the probability of a bit error is pretty small, in the order of 1,000th. So this assumption of approximating the summation to the very first term always holds.
I'm just a bit confused there. Is yp equals to 2 here? Like, but it didn't start on 1.
YT?
Yeah.
Okay, let me read out the problem again. Assume that the code corrects all the 1-bit and 2-bit error patterns.
Right.
So what this relationship returns is the probability of a message error. What is the message? It's a 24-bit word. Now, we are sure that the code prevents 1 bits or 2 bits. Now, if there's going to be occurring some errors in the code word, it's going to be 3 bits of error, 4 bits of error, all the way to 24 bits of error, right?
Okay.
So the summation starts from where the code is unable to detect errors.
And we minus it from one for the answer, right? Is it the answer gonna be one minus this summation?
One minus, you mean this one?
No, the answer for probably for 1 bit and 2 bit error, the answer for that, is it gonna be this one minus this summation?
We'll get to that point. No, one minus the summation, actually, if you're having a code word with a certain length, the probability of, which one did you say? Number 4? We'll get to that point.
Okay.
1 minus a certain number of bits of error refers to one bits of error let's say 2 bits of error. If you are asked to calculate the summation of these 23 situations, probability of the occurrence of 1 error bit, 2 error bits, all the way to 23 error bits. So what are the total number of situations? That's going to be all the 23 first probabilities plus the probability of all the bits receiving an error, right? So the probability of the occurrence of all the 24 situations is going to be 1, right? So if you are after the calculation of the probability of, for instance, the probability of these 23 first situations, you can add up 23 numbers, calculate each one of them, and then add up all of them together. Or you may find out what is the probability of this very last one and subtract it from one, right? So this is the whole thing.
So in this case, the first term you said is the answer, but does the first term start with t equals 0 or j equals 1?
J equals 3. We know that t is the number of the maximum number of bits your code can detect for errors, and then the summation starts from where we are not able to detect errors. So the detection of 3 bits of error and higher, right? So t is the maximum number of bits your code can detect. Well, not detect, actually correct, because if the code corrects 1 or 2 bits of error, then we won't have any errors associated with 1 or 2 bits. So the error would start from 3 bits up.
Oh, so if they said, like, if your code can correct maximum up to 3 bits, then you start from 4.
From 4, yes.
That's my question.
Yeah. So t is the maximum number of bits your code can detect and correct. Other question?
Yeah, so Professor, for the number of bits, if the last one's not 24 bits of adder, well, shouldn't the summation with 0 bits of adder be 1? Or is it,
This was just one simple example. We'll get to problem number 4 and then I'll explain that. This was just a situation. You've got the entire space divided into n situations, right? In this case, 24. So the probability of the occurrence of either one of, of all of these situations would be a total of 1. And if you're after one situation out of the 24, you may calculate this one. If there are 2 situations of interest, you would find the summation of the two, and if you're after just this one, or sorry, you're after all the 23 situations except for this one, you may find the summation of all the 23, or you just subtract the probability of this one from one. So the probability of no errors is this one, and you go all the way to all the bits, all errands. So no errors is one of the total space, and let me get to number 24 before, because I'm not having all the problem in my mind. Let me calculate the improvement in probability of message error relative to an uncoded transmission for a 2412 double error correcting linear block code. So the situation is, again, 2412, and error correction would be up to 2 bits. Assume that coherent BPSK modulation is used and that the received EB over N naught equals 10 dB. So the improvement in probability of message error relative to an uncoded transmission.
So which problem is this?
Problem number 4. So this 12 is the original number of bits, uncoded situation. And this is the number of bits for the code word that is actually after coding. Right? Error correction. One bit and 2 bits. Coherent BPSK modulation. And the received signal to noise ratio, EV over N naught equals 10 dB. Right? So performance improvement is improvement in probability of message error. This is what we are asked to figure out how much it is, right? So first, we have to find probability of a bit error. This is a bit error, and different from message error. This would be the lowercase p, right? this is the error function of square root of 1 minus rho times EB over N naught. The bandpass modulation scheme is BPSK. For BPSK, we know that rho, the cross correlation coefficient would be how much? Do you remember? -1. It's a kind of antipolar signal. So this is rho. EB over N naught is given, but it is in dB. So EB over N naught in dB equals 10 log 10 of EB over N naught equals 10 dB. So this term is going to be canceled out with this one. What remains on the right hand side would be 1. And this means that EB over N naught would be equal to 10. So now we've got rho, we've got EB over N naught. So probability of this error, the lowercase p, would be equal to the Q function of square root of 20. Q of 4.47. If you take a look at the table for error function, you would see that that table is for x less than 3.5, right? For above 3.5, use this approximation. Over x times square root of 2 pi times e to the negative x squared over 2. Now we are after the q function for x equals 4.47. So this p would be equal to 4.05 times 10 to the negative 6. So before going after each one of these situations for the code word errors or message errors, first we have found the probability of error for just one single bit. So for the uncoded case, what do you think? We have how many bits? 12 bits.
Yeah.
Probability of error for a 12-bit word so we have a summation, right? 1 bit of error, 2 bits of error, all the way to 12 bits of error. Each one of these situations with all the combinations that might happen will be error situation, error cases. And there's one more situation, and that is no error. So this is the entire space for the error to happen to this 12-bit code word. One situation is no errors, and there are 12 other situations which contain the occurrence of at least one error, right? So the probability of all these situations would be 1, right? So it's up to you. If you want to figure out what is the probability of the occurrence of any number of errors, you can find the probability of the occurrence of 1 bit plus the probability of the occurrence of 2 bits with all the combinations, all the way to all the 12 bits in error. So that is one way of finding the probability of the occurrence of error, no matter how many bits. The other is find out what is the probability of no errors happening. And then the entire space minus the probability of no errors. Right? So we have 12 bits. One case is no errors, and there are so many other cases in which one of the bits receives an error, 2 of the bits receive an error, 3, 4, all the way to 12. Instead of finding a summation of 12 terms, we figure out what the probability of no errors is, and then 1 minus that probability. So the probability of no errors in 12 bits, we know that the error in each one of the bits is totally independent from the error in other bits. So that way, the probability of no error in the first bit times the probability of no error in the second bit times the probability of no errors in the third bit times all the way to the 12th bit. Does it make sense? So 1 minus p is the probability of receiving a bit correctly with no error. And if you take it to the power of 12, then this term would be the probability of no error in neither of the 12 bits, and 1 minus that much would be the probability of any number of bits in the code, in the received 12-bit word. So p is how much? 4 to the negative 4.05 times 10 to the negative 6. And that's going to be 4.86 times 10 to the negative 5. So this is the probability of any number of errors in the uncoded situation or uncoded case. So this is before using the coding scheme, the 24, 12 coding scheme. And now we have to figure out what is the probability of message error after coding. The coding has the property of correcting 1 bit and 2 bits. After coding, probability of message error is the summation of j equals t plus 1, and t here is again 2, right? 1 and 2 bits of errors are both detected and corrected, so we start from 2 plus 1, 3, and we go up to 24, because in the after coding situation we have a 24-bit coding, right? This is the word that is subject to possible errors, right? It's not that just the 12 original bits would be subject to errors. Now, those 12 bits have generated a 24-bit code word, and that's going to be transmitted through the channel. So any one of those 24 bits in the code word might be changed by ear. So 24 choose j times p to the power of j times 1 minus p to the power of 24 minus j. And that can be approximated to 24 choose 3 times well, this one is supposed to be p asterisk. (24 minus 3) is going to be 21. Probability of a bit error after coding. What we should keep in mind is that before coding we had 12 bits, and now that is replaced with a 24 bits. And the duration of the code word after coding needs to be equal to the duration of the original work, right? So the bit time is half the bit time before coding. After coding, each bit takes half the duration of the bit before coding, right? This means that the energy of a bit is now reduced, assuming that the amplitude of the signal is the same before and after this coding, which is a correct assumption. Then if the bit time is halved, the energy of the bit is also halved. Does it make sense? So if the duration of a bit is divided by 2, then the energy of a bit would be the same, right? It is also divided by 2. Do you remember how we came up with the value of P, probability of error? We used ED over N naught, energy of a bit over noise, or noise density, and that was used for the calculation of the Q function. Now we have to repeat the same calculation for a lower bit energy. So this is the flow of what we think for this part of the problem. P asterisk would be equal to Q function of square root of, let me read it from here. Q function of 3.16. And now this is below 3.5. So from the table, we can look up the value of the bit here, and that's going to be 8 times 10 to the negative 4. Since the energy of a bit is now lower compared to the first part of the problem, probability of errors is now increased from, how much was that before? From 4.05 times 10 to the negative 6, probability of errors has grown up to 8 times 10 to the negative 4. That is a reasonable conclusion So this is P star, and this is the relationship that gives us the value of probability of message error. So Pm would be approximately equal to 24 choose 3, 8 times 10 to the negative 4 times to the power of 3 times 1 minus 8 times 10 to the negative 4 times 21, and that would be equal to 1.02 times 10 to the negative 6. Right, so this is after coding. How much was this probability of message error before coding? .86 times 10 to the negative 5. So the outcome of coding is bringing down the probability of message error by a factor of how much? 48, no? 48 times less probability of errors.
Could you go
Is it worth
over,
it?
could you go over like step by like a high level, not going over the math, just high level step by step of exactly what you did to get the question? Like step 1, I did this, step 2. You don't have to write this, just tell me. Wow, cool.
So we have the uncoded case, and we have the coded case. Before coding, we have 12 bits, or let's say a data word of 12 bits. What is the probability of error, any number of errors, in a 12-bit data word? So first, we find probability of a bit error. Then we go after the probability of messaging, P sub m. Right? Probability of a bit error is given by the Q function. Then we have 12 independent bits that are going through the same noisy channel. So the probability of, let's say, no error in this word is calculated first, and then based on that, we figure out what is the probability of any number of bit errors in our 12-bit data word, right? So this was what we did. EB over N naught was given. All we did was to convert it from dB to an absolute number, right? And then we were at this point. Now, the coded situation, we know that as a result of coding, now we have 24 bits. And again, as a result of the coding we're using, we are now capable of detecting and correcting 1 bits and 2 bits of error. So probability of message error is now the summation of all the possible cases with above 2 bits of errors, all the way to 2 bits. This relationship. Right? The reason this probability P appears here with an asterisk because it is not the same as the probability of bit errors like before. Why is that so? Because bit time is now shortened by a factor of 2 as a result of coding. So energy of a bit goes down by a factor of 2. The same happens to the signal to noise ratio. So probability of 1 bit error needs to be recalculated. We recalculated that and then we plugged it in this equation. Is that clear? Okay.
Sure. Two quick questions. So for probability of message error, it's equals to 1 minus 1 minus P, right? This is PE, right? The one you just calculated on the
This, yes, this is, see, the lowercase p that appears in this summation usually is the same capital T sub E we used to calculate, right? It's the same.
And another question, so when you're calculating the equation for solving for Q equation, do we use the table or the Q equation we have?
Well, it depends. As I said, take a look at the argument of this Q function. If it is below 3.5, use table.
Oh, okay. Oh.
If it is above that much, then use the approximation. Other questions? All right. So I think that's enough of coding. If you don't have anything else to raise regarding this problem, then we can proceed to chapter 4.
Could you go to question 4.4?
4.4.
Yeah, I don't understand which thing you're using to change the thing.
Oh, that is DPSK, differential phase shift keying. We skipped that in the lecture, so don't worry about that.
Yes, that is an implication. Could you go a question? Like, 4.7 has a very small thing, but I'll ask you after this, because is this an integral problem? I'm probably the integral, but could you go over 4.8 also, how you do the integral? The integral, I get a different answer.
Okay. So 4.7 first. What is,
4.7
4.7. Find the probability of bit error P sub B for the coherent matched filter detection of the equally likely binary FSK signals S1 of t is 0.5 cosine of 2000 pi t, and S2 of t is a cosine function with the same amplitude, but the frequency is 2020. Well, the frequency is not 2020. 2 times the frequency is 2020, right? So, and then the two-sided AWGN power spectral density n naught over 2 is equal to 10 to the negative 4. Assume that the symbol duration is 0.01 seconds. So this is the peak amplitude of a cosine function, 0.5. How do you find the energy of each one of these?
Repeat the question, sorry.
These are the two prototype signals, right? What is the energy of each one of these?
A squared t.
A squared t.
A squared t or a squared t, which one of those? Yeah, a squared t over 2.
So which one?
2. Second one.
This one. Can you explain why?
I did the math.
See, this one was for a constant level of capital A during the Big Bang. We used to see this in baseband modulation. This was the energy of the bit for a constant level A during the Big Bang. But now we're talking about sine waves or cosine waves. So the power of a cosine wave with amplitude A would be calculated by squaring the RMS value. This capital A is the peak value. RMS value is A over square root of 2. Then you square it. This is the power. Then multiply it by the duration of the signal, right? So this gives us A squared capital T over 2, right? So this is how we come up with that value for the energy of a bit. And it doesn't have anything to do with the frequency. This was one of the questions, as you may remember, we had in one of the exams.
Is there any advantage of doing it using the RMS value instead of doing like the proper integral from 0 to t, a cosine?
Well, if we were scientists, we would go after solving the integral. But after working with the same signal multiple times, we figure out this is one commonly encountered waveform. So we just memorize how to calculate the power of a sine wave without doing. Actually, we use just the result of the integral. We don't have to take the integral every time. So we've got so now we have two signals, S1 and S2. As you may remember from previous problems, probability of error for a bit, that is the same as lowercase p in the previous example. That is Q function of square root of 1 minus rho EB over N naught, right? So, EB was just calculated, N naught is given, and it remains the rho, which is indeed the integral of S1, S2, dt normalized by the bit energy, right? So we have EV, and we also have the two frequency or the two prototype signals. We have to take the integral. We're going to come up with 0.94 for rho.
Actually, Professor, it's that integral that I have trouble with. If you could.
This one?
Yeah.
Well, the integral of cosine
No, you get a
of
different
alpha
value.
t times cosine of beta t.
Yeah, you get a different value. You get like 1.94, and so does my calculator, and so does Wolfram alpha.
1.94.
So does Wolfram alpha, which is why I'm very confused.
See, what was the rho? That was the cosine of the angle between the two vectors associated with the two prototype signals. So can a cosine be above 1? Of course not. So rho needs to be anywhere between -1 to +1. So you should have made a silly
I don't know. I've made a
mistake, I'm not sure. So please double check, and if you can't figure out where the problem is, we can sit down together. All right, so from this point on, I think everything is clear, right? So now we calculated rho, and everything is known here, so this would be Q of 0.612, and from the table, it's gonna be 0.27. So let's get back to chapter 3 and see if there's any, do you guys have any problem with the problem set, or shall I pick one? We have already solved some of the problems.
That's going to be one of can you just repeat like why for cosine the EV is a squared t by half?
Well, basically, you have to take the integral.
Right.
But if you take the integral of a cosine function over one period, cosine function squared over one period, you're gonna come up with the amplitude, the peak amplitude squared over 2. No, sorry, the RMS, I'm talking about the RMS. The RMS would be the peak amplitude over square root of 2.
Yeah.
Then we know that the normalized power, the average normalized power would be the RMS value squared. And that's going to be A squared over 2. This is always true for sine waves, cosine waves, with or without phase shift. You might have heard, instead of RMS value, the effective value. I'm not sure what you were told in electric circuits. Was it effective value or RMS value? Both are the same, but sometimes one term is used rather than the other. So chapter 3, problem number 12. Did we solve this problem before or not? Do you remember? An analog signal is PCM formatted and transmitted using binary waveforms over a channel that is band limited to 100 kilohertz. So the signal is PCM. Channel bandwidth is 100 kilohertz. Assume that 32 quantization levels are used and that the overall equivalent transfer function of the raised cosine type would roll off, and the overall equivalent transfer function is of the raised cosine type with roll off factor of 0.6. A. Find the maximum bit rate that can be used by this system without introducing ISI. So we've got the bandwidth required for a signal to go through a channel with no ISI if there is a roll-off factor R. It's going to be 1 plus R times RS over 2. See, there's no mention of double sideband signals. We're talking about a PCM signal, right? So there would be a factor of 2 in the denominator here. The roll-off factor is given. And the bandwidth is also given. So RS would be 2 times bandwidth over 1 plus R. This would be 2 times 100 kilohertz over 1.6. And that gives us 125 kilosymbol per second. So this is the symbol rate. R sub s. And now we know that the number of quantization levels is 32 levels. This means that the number of bits per symbol would be log 2 of 32, and that would be 5 bits. Okay, so for each one of the symbols, now we have to consider 5 bits. See what else we are asked here. Find the maximum bandwidth of the original analog signal that can be accommodated with these parameters. So now 125 kilosymbol per second, and then we can, since we're talking about a PCM signal, what was a PCM signal? Do you remember PAM? A PAM pulse was a kind of coding on the amplitude of the signal for each symbol, for each pulse. We had actually n bits modulated on the amplitude, right? So the amplitude conveys those n bits depending on the height of the pulse. For the PCM situation, we said that there was also a picture in one of the slides introducing PCM compared with PAM. So those n bits can now be put by each other, whatever the values are. With the same amplitude. So the difference is in the levels of these bits, zeros or ones. So the same information that is conveyed using one single PAM pulse with varying amplitude depending on the value of those n bits. Instead of that, we have n pulses equal in height if they are a 1, and if they are 0, there's still a bit time for that, but the level would be at 0, right? So these are zeros and ones. Now that we have a PCM signal, this rate, 125 kilosymbol per second, means 125 bits per second. So each n bit now corresponds to a sample of an analog signal. See, the problem starts with this. An analog signal is PCM format. Let's assume that this is our analog signal. This signal is sampled with a uniform sampling rate. Each one of these amplitudes, the amplitude of each sample, is converted into digital, into n bits. And we know how many levels the quantization has. So this means that each sample is converted into 5 bits, right? So this one 5 bits, this one 5 bits, and each and every other sample is going to be 5 bits. So for each sample, we take 5 bits, we put them next to each other and send them to the outside. Right, so this one is going to be the PCM signal. If the rate of the bits is 125 bits per second, is it bits or kilobits? Kilobits. So this one is 125 kilobits per second. Can you tell me what is the sampling rate? Each one of the 5-bit packs represents one sample. So the sample rate would be 125 divided by 5 per sample. And this would be 25 kilosample per second, right? 125 kilobits per second. Each 5 consecutive bits actually represents one sample, and then the next sample, the next one. So if we divide 125 kilobits per second by 5 bits per sample, we're going to come up with a value for the sampling rate. So what was the sampling criterion?
I'm sorry, doesn't the question say 125 kilosample per second?
Yeah, how do you get from Sydney?
Yes. Since the coding is PCM, this is what I was trying to explain here. Since the coding is PCM, now each symbol is 1 bit,
Okay.
right? For PCM, each symbol is 1 bit, but if you're doing PAN baseband modulation, then for each pulse, you're actually stacking all the n bits you have in the PCM in one single PAN pulse. So one pulse would be the symbol conveying n bits. So remember, you have to pay attention to the type of signal in the cut. This was PCM. Some of the other problems we have already solved, say PAM, for instance, 311, 310, those are all PAM. So for that, the symbol rate is translated into bit rate by multiplying the symbol rate by the number of bits. Okay, so this is the sample rate, 25 kilosample per second. Do you remember what was the criterion for sampling, the Nyquist criterion?
I don't know, just over 2.
This over 2, yes. So the maximum bandwidth for the signal maximum analog signal bandwidth would be 25 kilosample per second divided by 2. So this is going to be 12.5 kilohertz. The maximum bandwidth for the analog signal would be this much if the samples are modulated into a PCM way and are transferred through a channel with a bandwidth of 100 kilohertz and a raised cosine filter of 0.6 roll-off factor is used. So part C, I know the time's over. Part C asks us to repeat parts A and B for the transmission of A to E PAN waveforms. So from this point on, when we come up with the symbol rate, now instead of considering PCM scheme, we have to go for PAM scheme, right? That would be the standard way we use to solve problems with PAM scheme. I'm sure you have it in your notebooks. If you have a problem with that, please come to me during the specified times. That is going to be tomorrow, right?
Can you make the exam easy since we only have 2 days to study?
Well, today we didn't have any new material. I just tried to reuse